Okay, here's a very short problem as far as the wording is concerned, but it's a little bit of a sleeper because it is a longer problem as far as the work is concerned. So it says calculate the density of sulfur trioxide SO3 at STP, then again at 1 atmosphere and 23 degrees Celsius. We're going to talk about what STP is here in just a second. That stands for standard temperature and pressure. So it looks like it actually wants me to calculate the density of this gas at two different conditions. So it wants me to do the problem twice, essentially. So let's figure out how to even calculate the density first, and then we'll worry about doing it twice. All right, so if I write down a formula for density, I can say that density equals mass over volume. And look, that V is something that we see in the ideal gas law. So I can, if I solve the density equation for V, then I can replace it in the ideal gas law equation. So let's do that. V equals mass over density. And then let's go ahead and change mass to grams. And you're going to see why I did that in a second, because it's going to come out to be something that's familiar. And so instead of M for mass, I'm going to use G for grams. All right, so let's go ahead and replace it. P equals G over density, and that equals nRT. Let's solve for D. So if I solve for D, I get pressure times grams, pressure times mass, divided by the number of moles times R times T. Now look, here's something that should be familiar to you. What happens if I have grams over moles? That should be familiar. Grams over moles equals the molar mass. And that's important because the question doesn't actually give us a lot of information as far as the number of moles or anything. But it does tell us the identity of the gas, and that's important. Because if I have the identity of the gas, then I can calculate its molar mass. So now I have a formula that says density equals molar mass times pressure divided by R times T. And so there's a lot of algebra that's going on there and a lot of sort of familiarity with the chemical concepts in order to get to this point where you have a formula for density and involving molar mass. Okay, so let's go ahead and take that molar mass in that density equation, and let's go ahead and calculate the molar mass for SO3. When we add it up, we get 80.062 grams per mole. Now I also need to convert the temperature. I have the atmospheres or the pressure in atmospheres, so I'm good there. All right, so let's convert the temperature. I get 296.2 Kelvin for 23 degrees Celsius. And so this is going to allow me to work on the second half of the problem. But what about the first half, the calculate the density at standard temperature and pressure? Well, what is standard temperature and pressure? What this problem is doing is testing your ability to memorize the definition of standard temperature and pressure. It's something you need to know. Standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. And what is 0 degrees Celsius in Kelvin? Well, it's 273 K. And so the only difference between the first half and the second half of the problem is they want you to change the temperature since the pressure is 1 atmosphere in both cases. And so let's take a look here. In the first one, density equals, now here's my molar mass, grams, 80.062 grams per mole. Looks like I'm going to need some more room. Put this pressure in here, 1.00 atmospheres. Probably going to need a little bit more room here in a second. Let me put my temperature in the numerator, 296.2 Kelvin. Yep, need more room. I'm going to put my gas constant, move that over, 0.08206 liters times atmospheres. Can move these up to the numerator, mole times Kelvin. And now I've got everything that I need. Let's check these units real quick. Kelvin cancels with Kelvin. Atmospheres cancel with atmospheres. Moles cancel with moles. I'm left with grams per liter. And grams per liter is density, mass over volume. And so the density at 23 Kelvin is 3.30 grams per liter. Now let's do it at standard temperature and pressure. Well, what was the difference? The only difference was the temperature. And so let's replace that with 273.15 Kelvin, run that back through our calculator, and we get density equals 3.57 grams per liter. Okay, that's it.